In section 1.4, we are going to start exploring mathematical methods to calculate limits rather than looking at the graph. So let's begin by looking at some properties or some laws. These are in your textbook. They are on page 35. So if you have the limit as x approaches some value a of two portions of a polynomial, let's say, so if it was something like the limit of 2x squared plus 3x, where f of x would be this portion and this would be g of x as x approaches like 3, let's say. Then the limit as x approaches some value a of a polynomial, or two items added together, is the limit of the first evaluated at that number plus the limit of the second evaluated at that number, assuming that the number a is in the domain of the individual components. Okay, so this would be like saying it's the limit as x approaches 3 of 2x squared plus the limit as x approaches 3 of 3x. And then you would evaluate each one at 3 and come up with a total. We will talk about that in just a little bit. This also works for the difference. A constant multiple, you can just pull the multiplier out the front. If you are multiplying inside the limit, you can take the limit of each one and then multiply those two together. Or if you have the limit of a quotient, you can take the limit of the numerator divided by the limit of the denominator, provided you're not getting 0 in the denominator. So let's practice some of those, and let's begin with just a problem I made up. So let's talk about the limit as x approaches 4 of x squared minus 16. Now, even though we're going to try to get away from graphs, I want to talk to you about the graph for just a minute. So if you were looking at x squared minus 16, and if you were going to draw just this portion right here, this is my f, remember, my f of x, my function, what would you be drawing? Well, x squared is a parabola that turns up, and minus 16 says it's one that's been moved down 16, so technically you would move down to minus 16 right here. And it would look like this. Okay, now it actually crosses at 4 and negative 4. Would you agree that those are the x-intercepts? So what's the limit as x approaches to 4? Is there actually a functional value when x is equal to 4? Yes, because this is a polynomial. Polynomials are continuous throughout. They don't have any asymptotes, they don't have any breaks, they don't have any starts and stops. They go on forever from minus infinity to infinity. There's no restrictions on the domain. So 4 is in the domain, which means that this function is going to pass through 4. So the limit as we get closer and closer to 4 is going to be approaching the functional value, which is 0. So what I can do is to say, all right, the limit as x approaches 4 of x squared minus 16, I can just substitute that in there and say the limit is 0. And see right here, as you come in from the left, we're approaching, remember a limit is asking for y, we're approaching 0. As we come in from the right, as x comes in from the right, we are lowering down to 0. So the limit of x squared minus 16 as x approaches 4 is 0. Now you don't have to put parentheses around here. Your book often does not. I prefer the parentheses, and I think it makes better notational sense, because if you just had the limit of x squared minus 16, it could be just the limit of x squared. And so I think this is a bit confusing, so I tend to put parentheses on there. I think you should too. Now let's talk about format for written information for your homework and for your tests. So if I say, here's your question, what's the limit as x approaches 4 of x squared minus 16? Remember, you can have 1 equals per line, basically is how you're going to remember this. So you could go over equals and then down, but you have to make a complete statement at the end. So whatever your majors are, whether they're pre-med, whether it's physical therapy, whether it's business, engineering, physics, math, whatever your major is, Calculus 1 is the first course, most likely, that is counting toward your degree. It is the course where you should be learning how to present your work professionally and in a nice, clear manner. So you may have had a lot of exposure to multiple choice questions and a lot of exposure to multiple choice answers, but you are getting into a field where you are held accountable for not only what you know and what you say, but how you say it. So let's learn how to do this professionally. So you always have to have your initial question. So in this case, the initial question is, what's the limit of x squared minus 16 as x approaches 4? Remember that without the plus or minus right here, it means from both sides equals 0. And so we would have to have a nice, clear summary. The question was the limit. The answer is 0. So be sure you have proper form. Some of the problems get a little bit more complicated. Let's do one more, and then before we get a little bit more complicated. Now again, if you leave the parentheses off, I think it sort of makes it questionable about what the limit's applying for. So put our parentheses here. Now it's pretty clear cut, the process that you go through to do limits, as long as you start off this process by saying, all right, there's that for appearances. If it appears one way, I have a certain process to do. If it appears another way, I have a different process. If it appears a third way, I have a third process. So the appearance of it, the way it first shows up, tells you what your process is. So if the limit that it's asking you, if the value they're asking you about, which would be a, as x approaches a particular value, if that value is in the domain of the function, then it's going to pass through that point. The y value of that point is your limit. So all you have to do is substitute it in, evaluate the function, and then that y result is the limit. So let's talk about this. Is 0 in the domain of x squared plus 3x minus 4? Now, that again is a polynomial. Remember, if it's a polynomial, there are no restrictions on the domain. And let's talk about the domains for just a second. When we talk about restrictions on the domains, many times we're talking about 0 in the denominator, imaginary numbers, things like that. So there's no restrictions on x squared plus 3x minus 4. It's a parabola. So it goes from negative infinity to infinity, so we can just substitute it in. So we would have 0 squared plus 3 times 0 minus 4. So evaluate the function at that x value. So 0 squared 0, 3 times 0, 0 minus 4 is minus 4. And we need to have a complete statement. So the limit as x approaches 0 of x squared plus 3x minus 4 equals negative 4. Now, so what would be my first rule, or the first thing I would wish to see? I'm hoping that every limit that I'm asked is a polynomial, because if every limit that I'm asking is for a polynomial, I just substitute in that x value. It's going to pass through that point. I get a lovely y value, and that's my answer. But as you can probably guess, they're not always going to be in the domain. So first thing is, in your next, and let's talk about your first test. The majority of your first test is limits. So you need this routine that you have hopefully prepared and memorized in your head, because you cannot have any notes. And you would look at it, and as soon as I ask you to do a limit, you go, oh, is that in the domain? If it's in the domain, I can just substitute it in. So always start off with that question. So let's look at problem number 16. That is in your section 1.4. It's a little bit more complicated. And we'll talk a little bit more about your format. All right. Now, remember, our first hope is that we can just substitute the number in. And we can, as long as it's in the domain. So let's check. This is not a polynomial. It's a rational function because I have variables in the denominator. What are your restrictions on domains? If you have variables in the denominator, well, you can't have 0 in the denominator. So would -1 get you 0 in the denominator? Well, -1 squared is 1. -2 times a -1 is +2. So 1 plus 2 is 3. -3 is 0. So yep, this is 0 in the denominator. So I cannot just substitute this in and evaluate it. So what I'm going to do is to try to see if maybe this is one of those ones that's like a removable whole that was discussed in section 1.3, where actually the value itself is not allowed, but I can see what it's approaching if I reduce it down. Because when they do the removable whole, if you read your section 1.3, what they do is they reduce it to a form that gives them the same graph and in a sense fills the hole. So let's see if we can reduce this. So one thing we might try to do is to try to factor it. So I'm going to show my work so I can get partial credit. I know how, and I'm very comfortable with factoring the denominator. So there's a lead coefficient of a 1. What multiplies to -3 and adds to -2? That would be -3 and +1. Now, if you look right here, this factor, that x plus 1, that's the one that's creating the 0 in the denominator. X minus 3 is okay because you could put -1 in here where x is. -1 minus 3 is -4. That's fine. -1 plus 1 is what's giving you the 0 in the denominator. So this is kind of the problem piece. I've heard people call them the problem child because, you know, these things are kind of like human beings or people. So this is the problem, and I'm trying to get it to kind of actually go away, right? So in order to get that to go away, I would really need to reduce it by canceling out something that's in the numerator. So let's talk about the numerator. It also, I hope, factors. Maybe you aren't as good at factoring this one as you are at the one at the bottom, but remember, if this is going to go away, it has to have an x plus 1 up there. So let's use that hope in order to help us factor. So if x plus 1 is actually up there, what would need to be the other binomial to get a 2x squared? You'd have to have a 2x here. And remember, you would have to multiply to 1, so this would have to be a 1 as well. So let's see if that would work. Does 2x times x get you 2x squared? Yes. 2x times 1 is 2x. 1 times x is x. Add those together, you'd have 3x, and 1 times 1 is 1. So yes, these are the right factors. This is perfect. So this that was giving me 0 in the denominator is a match to this one up here, and I would be able to reduce these two out. And in effect, evaluate it at this reduced form. So this reduced form would, in a sense, remove the whole. This would be what would be graphed, okay? And so I could see what I was approaching, even though it's not actually going to be a functional value. For the original graph, it is the value that I am approaching. And remember, for a limit, you don't actually have to get to that value, you just have to be approaching that value. So can I use the -1 now? Would substituting in -1 give you 0 in the denominator? No. So it's in the domain. So I would say it's 2 times -1 plus 1 over -1 minus 3. So I evaluate this by substituting in the -1. I would have -2 plus 1 over -1 minus 3. So this turns out to be a positive 1/4. Now, let's make a complete statement. because we are professionals and we are in Calc 1 and we can express ourselves in a complete mathematical sense. All right. If you don't box or circle it, I count off the points, okay, because you've got to learn how to do this in a professional manner. You have just got to learn how to be clear and succinct, because most of the professions that you are going into, if not all of them, you can kill someone if you don't write it down correctly and someone misunderstands your plan, your design, your computer program. If you don't have a nice, clear, concise summary of what you are expecting them to do, they may do it incorrectly, and maybe that's just going to cost you some money, but it could cost someone their life. So we have got to learn to be careful. All right. Now, format is huge. So let's talk about format. Do you have to show me every one of these lines? No, you do not. Could you theoretically, I guess, figure out what this is by looking at it and saying, oh, it's 1/4? Maybe. Okay, I wouldn't doubt that you could do that. I don't know that I could do that and be willing to count on getting all the credits. But remember, sometimes we do things that we look back later and go, what was I thinking? So be sure to show me enough steps to get partial credit, because sometimes partial credit can save you a letter grade. Also, until you actually substitute in the -1, so until you get to this point right here where you substitute in the -1, you have to keep saying limit. So this limit as x approaches -1, limit as x approaches -1, you have to keep writing that down until you substitute it in, because if you don't, you've changed the nature of the problem. It's like saying, what's the square root of 4, all right, versus 4. Okay, dropping off the square root changes the whole statement. Square root of 4 is 2. What's 4? It's 4. Okay, so without the square root, it doesn't mean the same thing. You have to keep saying limit until you substitute the number in, and then you drop off the word limit. Okay? All right, let's try another one. Let's do problem number 18. And problem number 18 says, what's the limit as h goes to 0 of 2 plus h cubed minus 8 over h? Now, the first question you should always ask is, can I just substitute in the 0? Would that be okay? Would that be in the domain? No, because it would give you 0 in the denominator, which means it's not in the domain. Okay, so is there some way that I can maybe reduce it? Well, this h does not cancel out this h, because this is a binomial involved in this cube. And remember your rule of order of operations that says you have to do parentheses, exponents, multiplication, division, addition, and subtraction before. So you would have to do this cube before you can divide. So you can't just divide into, there's a lot of reasons why not. This should look sort of familiar to you, because you remember the review that you did, the college algebra and trig review. This is why I had you do this review, so you would learn to factor, so you would remember, well, not learn, relearn to factor if you've forgotten or gotten rusty, and that you would remember some of these techniques we're doing in limits. So do you see how this is actually the difference of 2 cubes up here in the numerator? So let's try factoring again. So I'm writing down my limit because I have to keep doing that until I substitute in 0. So this is the difference of 2 cubes, where 8 is actually, well, it sounds like I just said that, but here's the cubes. 2 plus h cubed minus 2 cubed. And I'm fine, if you kind of make notes along the way, I guess, but you do have to just keep going down this one column once you set up this equals. So let's factor. So how do we factor the difference of 2 cubes? You find the cubes and then you drop the cubes. So you'd have 2 plus h minus 2. All right. So yes, we're going to reduce this in just a minute, but this is the going through each step of the difference of two cubes. You take the term in the front, you square it, and put it in the front. You take the term in the back, you square it, and put it in the back. You do not worry about your pluses and minuses. Front times the back goes in the middle. If this is a minus, right, if this one is a minus, this one is its opposite. This one is always positive, so you can put your signs in afterward. So let's see if we can clean this up. And the part that I'm actually, I forgot my denominator. The part that I'm actually wishing would go away is this one right here, because that's the part that's giving me 0 in the denominator. Let's see if it does. Hopefully. So 2 plus h minus 2 is actually just h. 2 plus h squared is 4 plus 4h plus a squared plus 4 plus 2h plus 4 over h. Everybody okay so far? All right, let's keep going. Now that I have a monomial times all of this over a monomial, now I can reduce it, and this h cancels out this h. So I have the limit as h goes to 0 of 4 plus 4h plus h squared plus 4 plus 2h plus 4. Now you can go ahead and add these all together because there are some like terms. Or now that you have what looks like a reduced form down to a polynomial, we could just substitute this in right now and then add them up. So I'm fine with it. Let's try that of substituting it in right now, because now this reduced form, h is allowable because I don't have a denominator. Now remember, h is not in the domain of the original function, but when I reduced it, this reduced form will tell me what I'm approaching. In the original form, even though I don't actually succeed in getting there because it's not in the domain. So substituting it in, I would have 4 plus 4 times 0 plus 0 squared plus 4 plus 2 times 0 plus 4. So this is 0, this is 0, this is 0. So this adds up to 12. Please remember to format your work correctly and to box and circle in your final answer so that you can get full credit. All right. Now, what this is saying is that I don't actually know what this original function would look like, but it is approaching 12 in the y functional value. Now, the concept about limits is going to come back over and over and over and over again, because it is the basis for taking the derivatives of functions, which we have a wonderful wealth of information that we can use derivatives for. So you may have heard about derivatives, but derivatives are actually limits. So when you learn some new derivative, they're always going to take you back to the limits. So you can never just go, all right, I'm just going to ignore this because I don't like this, and then maybe I won't ever see it again. You'll see it every time you turn around. So you really do need to practice limits and get comfortable and familiar with it. Let's look at number 23. All right, so this is the limit as x approaches 16 of 4 minus the square root of x over 16x minus x squared. So I'm not real sure what this is, but it's definitely not a polynomial, let's say. So can I just substitute in 16? Is 16 in its domain? Well, if I substituted in 16, I'd have in the denominator 16 times 16. Minus 16 squared, which would be 0. So no, I cannot just substitute it in. So I need to try to factor it. And do you see how in the numerator we have this lovely binomial with a square root in it? Do you remember that on your review you had to rationalize the numerator for me at one point? Well, this is one that's like that. So what we're going to do is we're going to say, well, I can't reduce it because the only thing that's in common down here is an x. And when I factor that out, that will not help. And it is not the difference of two squares. Well, you're going to find out at the end it kind of looks like that, and we're going to treat it like that, but it isn't right now. So let's go ahead and multiply it by the conjugate and just hope this helps. And you're going to hear me say this a lot, but blank is definitely wrong. Okay, so if you don't know what that you're supposed to be doing on a problem, if you leave it blank, it's definitely wrong. If you try something, maybe you'll get a few credit points for partial credit for aiming in the right direction. So don't ever leave anything blank. So one of the techniques, now remember, let's kind of review. The first thing you want to try to do is to take the value for the limit, the x value, and substitute it in. If it is in the domain, substitute it in and evaluate it. All right. If it's not in the domain, we would try to factor it and see if we can reduce it, which is what we did in the earlier problems. And if it has square roots in it, we're going to try to rationalize them and see if that helps. Okay, so by multiplying it by its conjugate, we're going to rationalize the numerator and see if somehow that's going to help with what is going on. Okay, ready? All right, so what have we got going on here? We have the limit as x approaches 16. And what would we have up here in the numerator? Well, 4 times 4 is 16. 4 times the square root of x is positive 4 square roots of x. Negative square root of x times 4 is negative 4 square roots of x. So that falls out. Those add to 0. And the negative square root of x times a positive square root of x is a negative square root of x squared, right? Which is what? X. Would you agree with the x? Okay, I think we do. Now what's going on in the denominator? So we already kind of talked about the fact that there's an x in common right here. So let's go ahead and factor that out. And do you see why we kind of liked that? Because this 16 minus x is what's giving me 0. When I try to substitute in this 16 right here, this is where I get 0. This term right here is going to be 16. This one is 16 minus 16, which is 0. But remember, we multiplied the top and the bottom by 4 plus the square root of x. So we already did that here and got this. But we need to write that term down here. Remember, we had 4 plus the square root of x right here. Remember? Okay. So let's see. Have we gotten anywhere? Because this is the part, this part right here, is the part that was giving me 0. So did it help rationalizing the numerator? Sure it did, because this 16 minus x binomial cancels out this entire binomial. So you can cancel out entire binomials, you just can't cancel out pieces and parts, right? So what have you got now? The limit as x approaches 16 of 1 over x times 4 plus the square root of x. Now, if I substitute in the 16 now, I'm not going to get 0 in the denominator, and so I can go ahead and substitute it in. So I have 1 over, put a 16 in for this x, 4 plus the square root of 16 here. So it's 1 over 16 times 4 plus the square root of 16. Square root of 16 is 4, so this is 8. So this is 1 over 128. So the limit, remember we have to write a lovely complete statement. Okay. So let's review for a second. All right, so what do we do when we see the word limit? We say, can I take that value for x and substitute it in? Is it in the domain? If it's in the domain, you substitute it in and get a value. If it's not in the domain, you say, well, is it a rational function? Can I factor it and reduce it? Does it have square roots in it? Maybe I can multiply it by its conjugate. And then one of the other techniques we had was problem number 25. And we had the limit as x approaches -4 of 1 over 4 plus 1 over x over 4 plus x. So remember in the review when we talked about complex fractions, and actually this 4 is over 1 and this x is over 1. And so we actually have 4 fractions inside one fraction, so it's a complex fraction. And the way that I would like to encourage you to clean this up is to look at all your fractions within the fraction, find the least common denominator. So this is 4, this is x, these are both 1s, so your least common denominator is 4x. So what you're going to do is to multiply the top and the bottom by 4x. But since you're going to multiply 4x by 2 terms, it might be better if you wrote it down next to each term so you can cancel if you're one of those people that likes to cross things out like I do. All right, so we have the limit as x approaches -4 of, now here we go. This 4 cancels this 4, and x times 1 is x. Everybody okay? Plus. This x cancels this x because they're monomials, and 1 times 4 is 4. So this one, well, 1 kind of cancels into everything by itself, so I don't have anything to cancel, so 4 times 4x. Now we could multiply this out and then multiply this x times this 4x, but can you see that this part right here is the part that was giving me 0 in the denominator? So maybe what I need to do is just hold that and not multiply it out. So what I might want to do is just keep this, because I can always multiply it out in the next step if I need it. So let's see if this helps. Does it help to not actually multiply out the part I'm trying to get rid of? Well, sure. In this case it did, because 4 plus x is the same thing as x plus 4. So this binomial is canceled out with this one. And I have the limit as x approaches -4 of 1 over 4x. Can I substitute in -4 now? Sure, because it will not give me 0 in the denominator. So it's 1 over 4 times the -4. So it's -1/16. So the limit as x approaches -4 of the complex fraction 1 over 4 plus 1 over x over 4 plus x is -1/16, which says the graph will be approaching -1/16 for y value, but it is not actually going to pass through that point because there's a problem with the domain where -4 is not in the domain. Now this is where we're going to stop for part 1 of working with limits. So let's review, right? So for limits, as soon as somebody says limits, what's the first thing you want to do? Is x in the domain? Is the x that's in question in the domain? If so, substitute it in. Okay. If not, okay, if it's a rational function, try to factor and reduce. What if it has, how would you want to describe it? Square roots, square roots. Let's just say square roots. Multiply by the conjugate and try to reduce. And then what if you have a complex fraction? Multiplying. Each term within the fraction by the least common denominator, the smallest thing that you can get everything to fit into. All right, now that's our list so far. So we'll develop a few more steps when you get to the next part 2 of 1.4, and then we'll have a few more things to do and to add in before the end of chapter 1. But this is the beginnings of our list, because like I said, the majority of the test is going to be find the limit of this, find the limit of that, find the limit of this other thing. So as long as you have this mental plan, okay, first I'm going to try this, then I'm going to do this, and if that doesn't work, I'll do this other, then nothing's going to rattle you, okay, either on the test or when you have to apply it in your future, because you'll always be able to call back this list. So memorize the list. Don't memorize how to do a particular problem like number 16 or number 23. Learn the list. What if it looks like this? This is what I do, and these are the steps on how to do it. So be sure that you have a list going for you and that you take the time to memorize it, because you don't have very many days to do this with it being a summer class. All right. So this is the first part of, like I said, 1.4. We'll do the second part of 1.4 in the next video.